Okay, we're going to work our way through this algorithm for calculating whether or not a given graph has a Hamiltonian path. So let's start with the input. Here we have an adjacency list. There's a couple different ways to represent a graph. One of those ways is an adjacency list, which we see here. So let's start by just trying to write down or draw the graph that this adjacency list represents. So 1, 2, 3, and 4 are the nodes. So we have node 1, node 2, node 3, node 4. And the adjacency list indicates to us where edges are between these nodes. So first we see 1, 2, 4. So this means that node 1 has edges between itself and node 2 and itself and node 4. So I'm going to draw an edge between 1 and 2 and 1 and 4. Similarly, for node 2, there's an edge between node 2 and 1, 3, and 4. There's an edge between node 2 and 1, an edge between node 2 and 3, and an edge between node 2 and 4. Node 3 has an edge between 3 and 2. Already got that. And 4 between 1 and 2. 1, 2. So this is the graph that is this is the graph representation, drawing representation of the graph described by this adjacency list. So we have this adjacency list, and we want to figure out, is there a Hamiltonian path? As a reminder, our Hamiltonian path says, is there an order of nodes that allows us to visit each node once? So we could have a Hamiltonian path that's 1, 2, 3, 4. Visit node 1, visit node 2, visit node 3. Oh, visit node 4. No, that's no good. That's not a Hamiltonian path because there's no edge from 3 to 4. There's no way to get from 3 to 4. Instead, maybe a Hamiltonian path. Let's see if we do, how about 1, 4, 2, 3. 1, 4, 2, 3. So we decided 1, 2, 3, 4. 1, 2, 3. Then we can't get to 4. That's no good. That is not a valid Hamiltonian path. But 1, 4, 2, 3. 1, 4, 2, 3. This is a Hamiltonian path, and therefore we say that this graph has a Hamiltonian path. So the question is, how do we calculate this? I have one algorithm here. There's other algorithms for calculating a Hamiltonian path. This is just one. It's simpler, on the simpler side. And what we're going to do is we're going to come up with a list of all paths. This is all orderings of the nodes that might be a Hamiltonian path. And we're just going to use this function called permutations. This is going to permute the numbers 1, 2, 3, and 4. So what we have is we're going to try and come up with all the different orderings. Right? So we could have 1, 2, 3, 4. We could have 1, 2, 4, 3. We could have 1, 4, 2, 3. We could have 1, 3, 2, 4, etc., etc., etc. Okay. So we're looking for, if we have 4 blank spaces, I want to put in order of nodes. Right? So this could be 1, 2, 3, 4. This could be 1, 2, 3, 4. We're going to choose nodes so that we could say, okay, well, that's a potential ordering. And the question is, how many orderings of nodes are there with 4 nodes? Well, we've got 4 choices for the first slot, 1, 2, 3, or 4. And we only have 3 choices for the next slot, right? Because we've used up one of our numbers. If we put a 1 here, it means we can only put 2, 3, or 4 here. So we've got 4 choices for the first slot, 3 for the second slot, 2 for the last slot, and 1 for the last slot. 2 for the last slot, 1 for the last. So the total number of options is 4 times 3 times 2 times 1, or 4 factorial. We have 4 factorial possible permutations of this of the list of nodes, right? So 1, 2, 3, 4, 1, 2, 3, 4. We already decided that one's no good. 1, 2, 4, 3, 1, 2, 4, 3. That's not a Hamiltonian path. 1, 4, 2, 3, 1, 4, 2, 3. That's what we had before. This one is a Hamiltonian path. So what our plan is, we're going to come up with every possible list, all the way 1, 2, 3, 4, all the way to 4, 3, 2, 1. Every different possible order, and we're going to check, do any of these orderings satisfy the Hamiltonian path condition? That's going to be our algorithm. So what we have here is we're coming up with that list of all possible paths, all permutations of the nodes on line 5. And what we want to do is then walk through every single permutation, all the different node orderings, and we want to check. We're going to assume that each path candidate is Hamiltonian, and then we're going to check, is there actually a way for us to traverse that order of nodes? Does such a path actually exist? And let's just walk through the algorithm now to see how this works. Now the only thing I'm going to do before we do that is I'm going to simplify this a little bit. Or actually, I'm going to make it a little more complex than it needs to be, but it's going to help us as we walk through. So I'm going to replace this here, and I'm going to make this a Boolean value that says has path. Has path to next. Next. And this next node is path candidate 1. The current node is the path candidate at I. And this is the edge list. Next node. All right, so what we're going to be doing, we're going to step through our path candidate, and we're going to ask, is the next node in the edge list of the current node? And if it has no path, if there is no path to the next node, then we're going to say this is a failed attempt and Hamiltonian is false, and we're going to have to then not print out that the graph has a Hamiltonian path and try the next path candidate. So let's see how this works with our debugger. Okay, so we start by initializing our adjacency list that we've already talked about, and then we compute all paths, all possible permutations. And this is 24, 0, 23. We've got 24 possible permutations of paths, which is 4 factorial, as we talked about. So we enter this for loop, and we're going to start with the first path candidate. And we want to take that first path candidate. That first path candidate is 1, 2, 3, and 4, as you can see on the right in the variable explorer. And now we're going to assume Hamiltonian is true. So again, in the variable explorer, we see Hamiltonian is true. And we now want to say, let's see if it really is true. So we're going to step through the path now, starting at I position, I equals 0. So I equals 0, and we want to say, okay, what is our current node that we're at? Our current node, again in a variable explorer here, says the current node is 1. Okay, and what's the next node that we need to go to? The next node is 2. This corresponds to our path candidate, right? Our current path candidate says we need to go from 1 to 2. Now we're going to look up our edge list. we're looking up in my graph based on the current node. Current node is 1. What's the edge list for 1? It's going to be 2, 4. Right? So now the edge list is 2, 4, and has no path to next. We're going to calculate, is there a way to get from our current node to the next node? And the way we ask this is there a next node in the edge list? If that's not the case, it means that there's no path to the next node, and then Hamiltonian will be false. So we're going to calculate this. Has no path to next gets false. Why is it false? Because the next node is 2. There is a edge from our current node to node 2. And that means there is a path to next. So has no path to next is false. Which means that this if condition on line 14 is false. Which means we will not execute line 15 and change our assumption that the Hamiltonian path is true. So far, from what we've seen, there is a way to go from node number 1 to node number 2. Okay, we're now going to continue along with our for loop. So we're going to increment I. I is now 1. We're going to update our current node. So our current node is now 2. Our next node is now 3. Right? We already got from 1 to 2. Now we need to see, is there some way to get from node 2 to node 3? And I'm going to calculate now this Boolean value has no next path. So there's no way to, is it true that there's no way to get from my current node to my next node? Well, our edge list says from our current node 2, there's a way to get to nodes 1, 3, and 4. And in fact, we're looking to go to 3. So this part is true, which means this whole thing is false, which means this Boolean condition is false. And we do not need to say that is Hamiltonian is false. So far, our path still looks good. It's still looking like we do have a Hamiltonian path, but that's about to change. So we now increment I again. Now I is equal to 2. We're going to update our current node and our next node. Our current node is now 3, and our next node is now 4. We're going to update our edge list as well. So our current node is 3. We're trying to get to our next node, which is 4, and we want to see, does the next node 4 exist in the edge list? Well, the edge list is just 2. So it's not, this is going to be false, which means this whole condition will evaluate to true. So this condition here, this if statement, is going to evaluate to true, and Hamiltonian is now going to be set to false because there's no way to get from node 3 to node 4. This is the same as what we saw in our graph. We went from 1 to 2, and there was a node to get there. We went from 2 to 3, and there was when we went from 1 to 2, and there was an edge to get there. Went from 2 to 3, and there was an edge to get there. And now we need to go from 3 to 4, but there's no edge. So our computation actually matches what we were doing in our drawing. We've detected that there's no edge between 3 and 4, and so we're going to say, nope, that is not a valid Hamiltonian path. So let's continue. We say, is Hamiltonian has no next path is true, so we're going to evaluate this. It means we enter the if statement. Is Hamiltonian gets false. Now is Hamiltonian is false. Now we actually are going to stop the loop here because we've already gone all the way up to the last node. We don't want to continue anymore. So that's the end of that for loop. If Hamiltonian is true, then we would print that the graph has a Hamiltonian path, but no such luck. So we're on to our next potential path. Now we've got 1, 2, 4, 3, and rather than sitting through the entire execution again, we'll see there's going to be 1, 2, or 3. That's not going to be any good. And we'll have to instead continue with our execution. And let's just fast forward to the end of our execution of our program. Oops. We've calculated all the way to the end, and now we see we did calculate the Hamiltonian paths. So there's a few caveats to this algorithm. You'll see that all we need to really decide is there a Hamiltonian path or not? But this is actually, even after it finds one valid Hamiltonian path, it just continues with the search. So we didn't really need to do that, but it makes the code a little bit simpler. We also, if we ever find a invalid path in the first step, we're going to continue. So if our path candidate was, for example, we started with node 3 and then we wanted to go immediately to node 1, we would immediately set is Hamiltonian to false, because in the very first step we're going to see there's no way to get from node 3 to node 1, but we actually still continue. So in order to see that, let's change all paths. I'm going to change all paths, and we're just going to explore one path in particular, 3, 1, 2, 4. Now 3, 1, 2, 4 is not a Hamiltonian path, as we can see in our picture. 3, 1, immediately we see there's no way to get from 3 to 1. So let's try executing this code. Here we see all passes 3. Oh, whoops. Hold on, let's just restart there. We want a 2-dimensional list because we're iterating through this. All right, so we're going to start with our first path candidate, which is first and only path candidate, which is 3, 1, 2, 4. And we're going to assume that this is a Hamiltonian path. We're going to step through this. And now we're starting with I equals 0. And our current node is 3. Current node is 3. Our next node is 1. So we're trying to go from node 3 to node 1. And the edge list only contains the node 2. So has no next path is going to be true. There is no way to get from node 3 to node 1. So is Hamiltonian gets false. Now is Hamiltonian has already been set to false. So really there's no point in continuing with our path candidate, because even if the steps from 1 to 2 and 2 to 4 are valid, the very first step we took is invalid. So if you wanted to optimize this program, we could just cut the search short here and say, well, okay, it's fine. We decided that you can't go from 3 to 1. I don't need to check the rest of them. But because our code is a little bit more simple, we're still going to check the path. Now we're checking the path from the current node 1 to the next node 2. And that is a valid path, but it doesn't matter at this point. We'll continue our execution. We'll get to the end, and you can see here that we did not print out any Hamiltonian paths if we're only considering this one path here. So now the question is, now that we understand how this algorithm works, the question is how much work has to be done to compute all of these, to compute a Hamiltonian path, to find out whether this graph has a Hamiltonian path. Well, this particular algorithm needs to do quite a bit of work. So it needs to check every single path candidate. So that's already n factorial, right? There's going to be n factorial path candidates. And then for each path candidate that we need to check, we need to step through every single edge one at a time, every single node, and check if there's an edge between the nodes every single time. So this line here is going to run n factorial, right? That like n exclamation point. And this for loop here is going to run n times because this for loop needs to run once for every single node in the graph because the Hamiltonian path touches every single node. So that means that this algorithm that we've written down here in code runs n times n times. And in terms of complexity, we can say this is O of n factorial times n times. As it turns out, we actually can come up with better algorithms for computing the Hamiltonian path, but this algorithm in particular that I've showed you is going to run in time proportional to the input of n factorial times n. So if it were just n, we would be running in time linearly related to the input. Instead, we have this big number here, which is n factorial n times. So it's a very slow algorithm.